Actually, to formally start, I should have been on my webpage, so I'm going to go over here and just say that we've just had a little opening before I started recording for the day. This video will get posted with the others that I have from 5 years ago on YouTube. It's part of the new way of doing things. I had a website that got taken down a year ago, and the campus made me rebuild it. And at that point, I wasn't thinking I'd be doing much teaching at all, but I decided to rebuild it with their help. And they told me videos can't be kept on campus anymore. So I went to YouTube, and now I have a YouTube channel that, just like any YouTube thing, I have subscribers from all over the world that I don't really keep tabs on, but they usually identify themselves when they're joining. So I've got not a lot of videos up, but more that could go up for other topics other than COM and DSP. So this is sort of the hub for the website, which is on the syllabus, is the hub for information and changes in assignments, assignment sheets, help sheets, and other such things. So when you come to the website, you will, this What's New was written quite a while ago, back on the 4th of January, but there's helps, like we'll be looking at things about setting up Python, setting up Julia if you want to use Julia. We're probably not going to do C++ development, but I have this made up because I used it in the DSP class. Various other links. So course materials, we're going to be studying the course syllabus here shortly. We'll be looking at the intro lecture as actually right after I leave here. And then you can see I've got the PDFs for all the lecture notes, and I updated the one for chapter 2. The other ones are old. That date of 2024 just means that they were reposted when the site was recreated. So, but those will start changing, and you'll notice that, and I'll write to you about that on the website, and I'll frequently, or most of the time, something significant changes, I'll also send you a Slack message on it. So I'll just use that as our medium. And I guess I'll jump over there just for a second, since I've got the app running here. Slack is basically a baby version, I'd call it, of what Teams does, because Teams tries to do everything for everybody, just like Microsoft Word is so bloated with features that it kind of bums you out after a while. But I have to use it where I work, use it all the time, and it's how I work, actually. It's how I work from home, is being connected with my team on Teams, right? And some of you have done that. I'm going to guess almost all of you have used it at some point or another. Slack is just, in my mind, is more low-key, and I created this back in 2020. It's called a workspace, and it's a free workspace. So any messages we put in on our direct channels, which are our one-on-one channels, or the class channel, and we have one for the lecture and the lab both, there's like an eraser running behind this 3 months lagged out. So the free version doesn't let you archive everything forever. It's running this window. So we're starting now, and it's going to be there, but then eventually things are going to disappear off the end before the end of the semester. It's not a big deal. I don't want to pay for it, and I do like its convenience, so I don't think you really notice it. It's just that if I put up a password, which I will be doing probably today yet, at home or something, I'm going to be putting up a password for getting into PDF files that have solutions and other things I want to keep security on. So you'll want to get that, and come 3 months from now, you might say the password's not on Slack anymore because it got erased because it was 3 months back. I'll maybe repost it again. I'll try to make sure it stays alive on the Slack channel for the class. At any rate, if at home you want to do a message session with me, a live huddle as Slack calls it, we can do that. You can share your screen. We can talk, all the stuff that you would do in Teams, and that's an alternative to office hours in my mind. I am going to hold office hours up in the lab right after class. I'll stay on campus for a while, but I don't have an office anymore. I'm not sure I'd want an office anymore because the building is getting all torn up on the inside. the engineering building up the hill. So I will only be here on this day. I bought a parking pass set. I want to start riding my bike again, but it was supposed to be a lot colder out, and I didn't want to take my e-bike over here. I live very close, but I'll start doing that again. And you guys, I'm making you come early for the class because I like getting it done with and move on with the rest of the day. Parking should be easy to get though, right? When you come early, it has a real plus to it. Last semester I taught really late at night, and I was going home and the campus had almost nobody around anymore. It was only 7:30, but it still felt very lonely to be here after 7:30. So this will get on, and then we'll get on with the lab. So in terms of Slack, though, the direct messages are perfect. See, it had this welcome card thing. So I was doing this to everybody. I was writing slightly different things. But I'm going to make this short and sweet. And I guess it sends a card to some people. I don't know why I did that for some and not for others. So Michael, you just got your response if you have it on your phone or something like that. And I like Slack because I can easily put it on my tablet, any computer, and of course my cell phone as well. Not that I want to be connected every second of the day, but this was kind of what we did during COVID. And you know, I'm trying to help keep you connected, but don't expect 24 hours a day action. It's there though, and it's there to help us out. At any rate, the other things that are maintained on here, like I said, these are the lecture videos that were from spring 20, the last time I taught the course. So I will start another column here of lecture videos, and it will be, I guess I'll say, decimated in a signal processing sense. I won't have but one per week because we're not meeting twice a week like we were in 2020. So it'll just be lecture one rather than A and B, right? Because we're meeting double time. We also will take a short break partway through this session. If that's any relief to you already to know that you can go to the bathroom, you can run to get a drink or whatever you want to do. But that will be maintained here. And like I said, this takes you to YouTube. Got problem set number 1 up here, which I've got a tentative due date on, and I'll talk more about that later. But this eventually will have another short sentence after that that says hints for sent number 1. So that's where I'm going to start putting password locks on things, because I respect the integrity of the book around the world, and I don't just want to share partial answers or hints for anybody except the people that are in this class. So you'll see a hints page get posted. I'll probably do that today, just get it up there earlier, and you can get a flavor for what that looks like. And what do you think I'm talking about? Am I giving you the answer? No, but I'm trying to give you, it's like you're standing there and saying, which direction do I go to answer this problem? I'm going to help vector you right to the right point. The first assignment doesn't have anything super challenging. It's all review kind of stuff from Signals and Systems, but it'll get more involved. In terms of using tools, I have a lot of Jupyter Python notebooks. I may create Julia notebooks as well, and I'll kind of get feedback today from you guys what you think about one language versus another. But the Jupyter notebook itself can host both programming environments. It can do Python programming in a Jupyter notebook. You can do Julia programming, and most everybody in here has used Python is my guess. Did I hear something, or is that a sound noise?
That was me.
Oh, okay. That was a tone. Okay. I'm thinking Signals and Systems all the time, sorry to say. So has anybody not ever used Python? Okay. And Julia, has anybody used Julia? Okay. So for those of you that haven't used Python, it's not going to be hard for you to learn if you've used MATLAB before. Julia and Python are languages similar to each other, and they're both similar to MATLAB because the idea is for scientific applications, and Python is very broad reaching. It has more than just scientific and engineering applications built into its libraries that you can download or packages you can install. But Julia is more focused on just scientific and engineering computing. It was developed more recently, about 10 years ago at MIT, and Python was created much longer ago, around 2000, in England. And the Python that's in the name of the language is not anything to do with a snake, although it now is, you'll see logos that have a snake or something in Python, but it has everything to do with British comedy. Monty Python, has anybody ever heard of any of his stuff? So the guy that created the language liked Monty Python. So most software people and engineers, I think, we have a good dry sense of humor, and we have strange humors and all kinds of other strange things that we think about. So you'll get into it. And the Jupyter Notebook is a web-based environment, and I'll be showing you that later. You also end up learning a little bit about Markdown. Has anybody written in Markdown? Where did you write in Markdown, just out of curiosity?
GitHub repos.
Okay. Okay. Yeah, it shows up frequently there. So, and it also shows up in other documentation environments too. It's simplified HTML, something that you may have learned in high school, possibly, or gotten familiar with it. It's a tagging environment, so it's very logical the way it works out. So I have several of them up here. This one for chapter 2 is one we'll be looking at later today. It's been enhanced for today, whereas the other ones I will have to do some rework on them. They're still good and everything, but I want to do some updates to them. And I've already updated this one. I haven't pushed it up there yet, but if I make more changes or anytime I'm doing things either at home or do things in a lecture, and I feel like, hey, I did this and I helped get you started on a problem, I added it to an existing notebook, I will push the notebook again so you can go grab the latest one. And if I don't have it up there right away, you can bug me on Slack and say, hey, you showed us something that would be helpful in working this homework problem. Can you get that up there? And I can then do that. So you can help me out because I won't remember everything that I want to do. I do have projects in here in Python that I've used in the past, back in 2020. Just take a quick look at this one. This one is kind of more digital communications oriented, which is not the primary focus of this class, but this one just gives you an idea of a kind of a messy looking block diagram, messy in the sense that it's showing both the transmitter and receiver. It's showing a lot of digital signal processing aspects. And to work this project, the way the example code is set up, it's in a Jupyter Notebook, you can use it as your starting point. So what I do very frequently is I don't say, you know, you're taking a programming language class, you're starting from absolute scratch. Do you think engineers do it that way all the time? Start from nothing? I mean, we have AI on our web browsers, right? So it's thick with ideas on how you're going to code something. Now, understand when you type in something, I want to do such and such in Python, and Python is such a popular language that it's got lots of AI, you know, threaded into it. So the way I think of AI, when I type something into my search window and compose it in a certain way, it will write me a little article about what I want to do, and it'll give me some code samples, and then, of course, it gives me other links around it that it formulated its article from. But you will get lots of good Python code. Now, will it always work? Maybe not. I mean, AI is very bold. It's probably the way you want to kind of be. You don't want to be so arrogant when you go to an interview that you just make the person interviewing you think you know any and everything, and you're just infallible. But AI tends to, you know, when you get your thing written in the browser, my impression is it's trying to tell you that this is it. I mean, this is just the real thing. It's perfect. What do you guys think? This was an open question, but about the use of AI, I'm not against using it, but you do have to what? What are some rules of thumb or just some thoughts that any of you might have when you're using it?
I use a lot of AI for work, and so one of our best practices is kind of reviewing everything with AI, and then without it to kind of say, hey, like, where are some vulnerabilities in the code? Oh, all of a sudden this AI just exposed all of our passcodes or something like that.
Okay.
And so, yeah, review.
Okay, so you used a term that's used in a lot of different contexts, but best practices, I've heard that a lot. Some of you maybe have heard that, but best practices are what they say they are, and they're different depending upon your context, but practices, and we're in charge, engineers are in charge of so many things that the rest of our society relies upon. We cannot be giving them bad stuff. I mean, that's one of the things that I was taught. I used to teach capstone design in the program. One of the things that engineering is all about is helping our society in general. I mean, we're trying to make the technologies and things we study to develop products and services and so on and so forth that helps people out. We're not there to destroy people. And admittedly, if you play video games and other things, there's a lot of that goes on in video games. But I don't play video games, but I have a son at home that plays PS3 and the other, or whatever PS generation he's on. A lot of destruction that goes on in those games. But we're so closely tied with the technology that gets out there that we got to be accountable and we have to have integrity. So at any rate, you see a lot of block elements in here. This is not unlike, the real thing. And so in this project, and I'm probably going to use some variation of this project, you will be working all the way through a communications link that starts with a data source, which would be an RF front end is in front of that. And then in this case, it's all discrete time processing based. So the transmitter has a data source that then does some digital signal processing with pulse shaping in the P of N, which is an impulse response, a pulse shape of some sort, generally as a square root raised cosine filter, which we'll talk about. DAC is digital analog converter, right? So we're going out from digital to analog, and then we're going to mix it up. We're going to learn about the mixing process, multiplication process with sine and cosine, and we form a transmit waveform at a radio frequency. And we do that using some RF and analog circuitry that's in our transmitter, and then we send that out to the radio. I didn't set my timeout, so I'm going to have to keep moving my mouse. And then in this case, we had the possibility of adding in, I'm talking about, I guess in this area right here, talking about adding in and adjacent channel signals. And then finally, the channel also consists of white Gaussian noise, and we'll be talking about that. You'll see that in problems and in simulations. What do you think that represents in reality? I mean, we're systems people, so we're modeling at a higher level, but physically, what is white Gaussian noise, especially a device person?
Cosmic microwave background radiation.
It could be cosmic. That would be more or less what would come in on an antenna, but it would be just fundamentally the thermal noise due to random electron motion in our receiver front end. And it produces the random electron motion. If you've had prob stats, and some of you maybe are just taking that, 3610. How many of you had 3610 already? So do you remember something from 3610 called the central limit theorem? So if you have a random electron that's just agitated because it's not at absolute zero, it's bouncing around, it's creating some thermal noise voltage, but you have many of those electrons that are bouncing around, you get that distribution tends towards, when you sum a bunch of independent voltage sources together, you're going to get a Gaussian distribution or normal distribution. And we have a whole appendix on that, Appendix A in the book and in the notes, is on thermal noise modeling in a receiver front end. So that's more of an RF crossover topic, but so that just represents the fact that the signal is not going to be really strong when it arrives at the receiver, and there's going to be a noise floor established in the receiver front end. But in our simulation model, it's just added directly in, and I'll get that in Python using a random number generator, or in Julia, a random number generator, or in MATLAB, pick your languages that are out there. So we'll model the impact of a weak signal, and that's how we always communicate. We set up what's called a link budget, and that's part of Appendix A eventually, but a link budget so we don't transmit more power than we need to. Why would we not want to transmit more power than we need to? I'll just think of our cell phone.
FCC regulations.
FCC regulation fundamentally, but why would we not want to transmit more power than we need to just to make this last the day? We don't want to suck the battery down, right? So we transmit just enough. We take into account other factors. That's coming up in some slides I've got here, but so we have it weak and it's close to the noise floor, and it's going to be buried in noise in some cases. So then we come into the receiver, and in this case, the signal comes in through a bandpass filter, and this would probably be an RF microwave filter. And then it gets mixed back down with another pair of multipliers, sine and cosine. We'll learn about quadrature signals, and we're going to be talking about sinusoids in the very beginning, just some reviewing, but the fundamental signal in communications, signal processing and radios, if it's a DSP-based radio, it's called complex baseband. So complex baseband means the signal is not shifted up to a carrier, and I'll be reviewing those topics and talking about that. But it does have two components. It has an in phase, which is the real part, and the quadrature part, which rides when we demodulate or multiply by the sine. That's the imaginary part. So we have a complex signal. So when you study signals in systems, mostly prior to this, you're thinking of a real signal, right? Communications waveforms, generally now in the processing, it's all complex. We have a complex baseband signal, and it's not complex. This is a pun, I guess, on, play on words, right? Complex is a mathematical complex variable, let's say. But complexity is something that shows up in engineering. So if it's not complex to make it hard, it's just, that's naturally the way it unfolds. So complex signals will be a new thing. We'll be talking about them a lot. Then we eventually go into the low-pass filter to protect from aliasing effects, and then analog to digital converter. And then now we're back at this CPX, meaning complex, fully complex, real and imaginary part, and then we carry out the rest of the processing using complex or INQ samples of the signal. Now, I spent a lot of time on that, but I just wanted to kind of pull something out of a project. And in this particular project, we're talking about the complex signal. The signal we actually send is a quadrature amplitude modulated signal. So amplitude modulation is the first modulation type we'll talk about from its very beginnings historically, but it's now extended off to waveform types that are used in things like our Wi-Fi, in cellular, and other applications. Probably Wi-Fi really made this famous, and cable modems made this very famous too. How could you get lots of information sent down in a given bandwidth? And that means something to all of us, right? We have some internet connectivity in our home or apartment. So this is called a dense modulation scheme. So every one of those red dots represents a point in a complex plane. The real and imaginary parts now carried by a microwave carrier or on a lower frequency carrier on a cable or free space in our Wi-Fi. But each one of those, and this 64 QAM, so we have 8 levels horizontally, and we have 8 levels vertically, so we have 64, what's called 64 QAM. We have 64 total points, and each one of the points represents 6 bits, because that's the log base 2 of 64. So each symbol, as it's called, carries 6 bits of information. Is that cool? I mean, more bits per sample means higher throughput, means more capability in our web browser or whatever we're trying to do. So 64 QAM, like I said, is what this represents, and it has a decision boundary around each one of those points where we have a slicing action that would be done in DSP, or it could be done in an analog system where we make a decision because it's going to be noisy. It's going to be received with noise on it. I think I might have a picture of it in here. Maybe not. I don't. But it's going to have some noise on it. So we have to set up a thresholding scheme, and then we have the nearest neighbors around that. And I'm kind of I'm going off on a bit of a tangent just because I'm feeling like it, right? I'm not so rigorous with my thinking that I can only do one thing. I'm trying to just kind of get you in the mood or whatever.
I saw that we were looking at BPSK. For BPSK and QPSK, do they have the same performance?
Ideally, but that's ideally, in other words, if the in-phase and quadrature carriers, the sine and the cosine, I'm thinking of those as a cross because I'm saying cosine projects onto the real axes and the sine carrier makes the signal project onto the imaginary axes. But if they're not perfectly quadrature, and an RF component might have some imbalance, it's called phase imbalance, where it's not perfectly quadrature. And then you project a little bit of interference onto the opposite I and Q, meaning that QPSK, which is quadrophase shift keying, 4 phase states, will have some interference, whereas binary, just having plus and minus 1, wouldn't have any chance for that to happen.
Okay.
But why would you use QPSK? And I'm rambling really sophisticated terms already. 2 bits per symbol. This one is 6 bits per symbol. Higher density means more throughput, means happier customers or whatever. Do we need all this data? I sometimes wonder, do we need all this data? But, I'm just saying that facetiously. As an engineer, what do? We supply the needs of our consumers, and we're trying to give them what we think they want. And we want to watch a live stream of this or that or the other thing. We need all this capacity, but what's a limit on it? I don't really know. I'll say more about that a little bit later. But okay, so I got a little bit sidetracked from that. I'm now going to just say the other thing that's in here, I will eventually have sample exams in here with solutions prior to us having an in-class exam. So I do that, and so that's kept on the website. So I'll do more touring on this if I feel I need to, but now I'm going to jump over to the first chapter, and the first chapter just has this block diagram at the top from the course, but I have it integrated into the lecture notes, so I'm just going to do that. And if you download this, these are links. They're not active right now for whatever reason in this PDF viewer that I have. But so one of the things that I always like to do, even though I'm not a professor teaching as a full-time faculty, getting paid as a full-time faculty, I always would give the course perspective, whether you're a graduate student or undergraduate. My hope still is that they're going to hire somebody and they're going to start teaching more of the comms and DSP classes other than just one per semester. And it also lets me talk about how it fits into the other courses you might still be wanting to take. We'll go over the course syllabus, then my instructor policies, we'll go over that. The syllabus we'll look at that separately because I have a lot of links in it. That's probably one of the most important things to do from a housekeeping standpoint, because when you take a course, I have to provide the rubrics that I use for grading you in the class, and that's in the course syllabus. That's kind of like a contract, how we're going to operate this thing, and how this stuff works. I'm then going to talk about how this course relates to the lab, I'll just tell you right now, they're strongly coupled together. One helps the other. It's not a one only helps the other. They both help because hands-on, I learned by hands-on. I was in a family of amateur radio people, so I did a lot of hands-on stuff long before I even thought I'd become an engineer. And learning by doing and hacking, making electronics projects was kind of something that I did as I was growing up. And I'll explain more as we go along. Not everything I did was legal. It's just something that you do when you're playing with radio frequency stuff. Bootleg transmitters was something I kind of got into. And at my college I went to, I actually built a transmitter for a radio station that operated by students until I was shut down. But the dean of students threatened me and my peers or whatever, that if we didn't shut off our bootleg radio station, we wouldn't graduate. So
Pirate radios.
yeah, it was a pirate. Yeah. But there's more to it than that. We were competing with another dormitory on the campus, so we wanted to have a good signal out there. And I wasn't a DJ very often, but the people that played the music and did the talking on the radio were, they were the actors, you might say. They came in and did their show or whatever and played music, but I was a technical person behind it. And the antenna is still in the dormitory as far as I know, because I put it up in an attic of a very old dorm building, and no one would want to climb up there and find it, but it's an amateur radio antenna actually. I mean, only certain people would do this, but I was one of those types. But I was paired up with mechanicals, so I wasn't. I went to schools of mines, is where I got all my degrees from. So I was with lots of other engineering discipline types where I went to school. So we'll talk about relation to the lab, software tools. I'm really big on tools these days because I didn't have them growing up, and when I was a student. So I grew up having a mainframe computer as my computing device and a pocket calculator. Those were the only things I had. But now we have so many things we can do on the computer, and there's so many modeling tools out there that gives you a flavor for exactly what you're doing. And if you're a visual learner, you can rig up a quick little Python simulation, you can plot it, you can visualize it, and it's very valuable. And when I say visualizing, one of the things I'll be getting into is the fact that in communications theory, we don't look at just a time domain waveform. We're almost always looking at the spectrum. And you mentioned the FCC. The spectrum is so vitally important. The Federal Communications Commission regulates it in the U.S. We haven't talked about that in another slide, but we have to see what we're transmitting. I was in a meeting yesterday where I'm working right now, and I'm working on some lunar-related projects. I was working a year ago for a space radio that was destined for, now my brain's drawing a blank, Amazon Space Company, what's the name of it again?
Blue Origin?
Yeah, Blue Origin. I was working on a Blue Origin project on a space radio for a project called Blue Moon, which is a lunar transport device. And I'm working on LunaNet, which is another project related to Moon.
On a semi-related note, I found the book online on a PDF and I posted on the Slack.
Okay, I'm not endorsing that, but I have a PDF of the book too. That's how I use it.
On Amazon it's $167 for the ebook.
Yeah, but most of you get it through TAP, right? Or some of you do. Which I think I've enabled that by accepting pushing out there my profiles for, what's the name of that thing that most other professors use? I don't use it though. Canvas. I pushed it out there, and I think that enables TAP. Let me know if you rely on TAP. This last semester I did that, and everybody got their TAP version of the book, and that made everybody happy. So, okay, and sharing, just like what he said, share if you want to on the main channel. That's our communications medium to discuss amongst ourselves as a class. So go ahead and do that. I'll also talk about how it connects to a COM2 class, which hasn't been taught for a while, but I'm just anticipating it might be taught next fall. And then I'll give some background information. So this might be pretty small. This was something Dr. Platt, who teaches and controls, had created for his classes, and I decided I would just give you a perspective that Communication Systems 1 is hidden way over here, but this is your entire undergraduate curriculum. The other class that I frequently teach, the one that I've taught the last 2 falls to help out, is Modern DSP. I look at these as being very connected. In the olden days, you learned circuits, and you still learn circuits, right? If they ever take that out of electrical engineering, we're no longer electrical engineers, but not everybody works directly hands-on in circuits. Some of you were mentioning that in your discussion, you're thinking of circuits. You soon find out that a lot of us are working entirely doing software. Now, is that a crime? That's another good discussion question, is just doing software modeling and developing firmware and things, either for FPGA or embedded systems. I think it's acceptable. You have an interface to the analog stuff. So modern DSP relates very heavily to the way communication systems get built. But low-cost devices, and I'll show one at the end, are very tiny, and they can just do things with a few analog parts to be a lot less cumbersome than a full-up digital radio would be. Other things that are connected, though, not immediately connected and not a prerequisite for this class, is prob and stats, but I'm going to be throwing things out in modeling and things where we do use random number generators. So if you're taking prob and stats this semester, it will be helpful. If you've already had it, it'll definitely be helpful because it just expanded your horizon. You know, every class you take in engineering does what? Expands your mind into this subject matter. And I used to teach, let's see, where is it in here? My throat's getting dry, so that's why I'm almost choking. Signals and Systems 1. I can't see it in here. I used to teach that class. It actually, that's a good time for me to mention, that's what led to me writing this book. So if you need a review of continuous and discrete signals and systems, I wrote that book on a commission, not because I wanted to become a dummies author and make a lot of money. I haven't really made any money on it, but they paid me to write it. I haven't sold enough copies, but it's available out there. It's about $20, I think, or maybe $50. You can go ahead and pass it down just so that you can see it. But at any rate, that is the deterministic stuff is definitely the foundation for what we're going to do here in Com Systems 1. This is the flow as it was when I left in fall 2022. I hope to be helping the new person, who's still a virtual person, get into this. So we are right here, and it's directly tied to the lab. Other classes that follow would be COM2, and still other classes that follow would be statistical signal processing, real-time DSP. These are all other classes that were offered in this area at one time or another. But sadly to say, it's really only been these 4 are really the only 4 that have been offered regularly since I left. And that's why you see them on the website, because when I started reconstructing the website, I said, I got to get these back out for the people that I'm coaching to teach these classes until we hire somebody. But there's a lot of other things that could happen, and especially if you'd be a graduate student, you'd say, where are they? And I'd say, as a former full-time faculty member who wants to be an advisor for a master's or PhD student, I want you to have these courses so you can write your thesis and do your work. If you're going to make this your area, I still hope it happens. So I don't understand all the politics involved, though. Any questions on this part of it? Stay tuned, though. And it doesn't matter for the most of you, though. You get a chance to get exposed to the math and modeling side in the lecture, and then you get exposed to the hands-on and test and measurement side in the lab. And those are very vital. As a matter of fact, the lab is, I've had people in industry say that if I can hire somebody that's been through this lab using all this test equipment that we're going to use maybe in a grander scale in the company, I don't have to spend a year training them. They've already got the lab experience. So I've been told that from multiple people. And recognize the fact that certain things on your resume do make a difference. The good news is the grades you got in all the classes in the end are in your rearview mirror as you're driving that way, and you don't even notice them anymore at some point. Yeah, having a good understanding is important. You need to be competent at doing your work, but don't be confused thinking that grades mean everything. The ability to do the stuff and be motivated, and fundamentally, I always talk about having a passion for this material. You didn't invest this much time to not have some passion for the subject. And I guess thinking back to what I started on and then lost track of when I started passing the Dummies book, whenever I teach Signals and Systems 1, people would be really naive and really fragile. And then about a year later, they don't even want to talk about where they were when they took that class. It's like, I'm not an infant anymore eating baby food. I'm now growing up or grown up, right? But every stage of your life, there's always more to go to. But you mature fast in a 4-year program. I'm going to jump over to the web browser for this part of it because, to me, I can hit the links on this. So, like I said a while back, I will be using AEC 318, which is where the Comm Lab has now been moved to. It was moved just a couple of weeks ago because its old location next to the lounge in the engineering building is now in the demo phases. It's going to get redone. But I've been told that this lab is probably going to stay in that building because there was a space for another communications research lab, and I said, that professor left before I did. The junior faculty, to me, left. That's another thing that happened that really disturbed me. The junior was going to inherit the keys to my kingdom, if you want to call it that. He bailed out of here 6 months before I did, which is like, you get out the door faster than I can. There's something not right about this. But at any rate, he had a research lab. He had funding. He gave that all up to go do something else. And I said, let's take over this lab because if we have a space that was allocated for something with communications, we better occupy it so somebody doesn't take it away from us. So I managed to convince people to do that. So the book, I'd recommend the e-version. You said that's $167. I think the TAP is probably the best. That's what students told me last semester in DSP. I can't find my paper copy of the book, actually. I don't even know if I should have kept one. But I do have the PDF version. So I'll let you deal with that. Let me know if you're having issues, especially those of you, how many of you use TAP books? Can you get the book? Is it there? Go find out and let me know if it's something hasn't worked right with Canvas. I just passed around the Signals and Systems for Dummies, which actually has 4 chapters on the internet. It's got 1 chapter on communications examples. Modeling software, I think I'm going to just settle on Python. I'll maybe do some Julia demos using the Pluto notebook, which I'm really fond of. It's called Pluto, which you're saying, wait a minute, this was invented about 2 years ago by a German guy, because he said Jupyter needs a notebook, Julia needs its own special type of notebook for doing development and writing documentation. I'm going to call it Pluto. He just created that name. But Jupyter, if you notice the spelling of it, don't think that's how you spell the planet Jupiter, right? It's got the Y in there. Does that bother you? Okay, there's a story behind it. The JU is for Julia, the PY is Python, and the TER, I've even forgotten what it was. I used to go to the scientific Python workshops every summer down at UT Austin, but it was written to host different programming environments. So Julia and Python are definitely supported, and I'll be able to show you Julia and Python notebooks running in Jupyter. So, okay, the contract. This guy right here. Wait a minute. Sorry. If I want to draw on this, I got to do this. So this is the plan for the semester. Graded short quizzes and or homework assignments totaling 20%. How am I going to make that happen? I'm still pondering this. In the past, though, again, because I don't get any grading support of any kind, I want you to learn things, and I want you to be have a lot of practice for taking exams. So I'm definitely doing the homework assignments. If I decide to opt out of the quizzes, I will have you turn in selected problems, and I'll let you know, not with a huge amount of advance warning. I'll let you know, oh, on this next assignment, I want you to turn in bing, 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 and that's what you'll do as a PDF on Slack. So you'll have to figure out how to get a PDF to me on Slack so I can grade it on my iPad, and I have some suggestions on that, which I'll get to eventually. Some of you have this perfected, though I know last semester I only had 4 people. Everybody did it differently, and it worked. If when I get a PDF on my iPad and I blow it up, using my pinch or whatever Zoom thing, if it's really faint and really tiny, I'm going to be very aggravated trying to grade the paper. So check that out. If you use your cell phone, just scribble something down and then take a picture of it and convert it to PDF. Make sure it's readable. A lot of you use tablets, though, and I just see really excellent papers if somebody uses the Apple Pencil or something like that. I'm going to suggest other techniques because you're going to have to fuse together handwritten or typeset versions of problems along with some things from, say, a Jupyter notebook, and I will have a technique on that. I'll just jump over to that for a second right now. If I was to go up here, and I'm going to move a copy of it from 5650. This is something, I'm going to move this exact tab over to 465625, but this is a tab that shows you how you can use Typest, which is a cloud-based editor to put together your homework. You can merge PDFs, you can merge Jupyter, and I'll get you going on this. You can look at it. Now you're saying, you're crazy, no one would do this. I had one person that went absolutely off the charts with getting into this. He did his resumes, he was he got way into it and did a fabulous job. I had another person that said, oh, I just want to be able to take my PDF snippets and put them in a nice document, and this shows you how to do that, and then I want to be able to take snippets from my Jupyter notebook and put them in there and organize it, and he did that. He's very minimalistic, a student athlete who, by definition of a student athlete, means he's busy doing a lot of other things. He did really great with that version of Typest. Person number 3 used her iPad for everything and cut and pasted snippets from Jupyter notebooks. person number 4, he was, a really smart guy, but he was also economical with his time. He used Word, scribbled out his homework, pasted it into a Word document, and exported it out as PDF. He did that, and then he put in, the snippets and things from Jupyter, and that worked fine for him too. Could I convince any of them to try something else? No, I'm going to do what I've done. You're all seniors or graduate students. You have a routine, and I'm trusting you to come up with something, and you can make it work. You're not a rookie at it. You're not doing it for your first time. But exploring, one individual, he jumped on this types thing, and I will look at that in just a second here. So quizzes, 20%. Computer projects, there will be 2 of them worth 20%. The projects allow you to team, so I'll specify how many you can have on a team. If you're a graduate student, you don't get to be on a team. You have to do it by yourself. I have to differentiate, and I'm entitled to differentiate between the 2 types of students we have in the class. So that's where I'll draw a line. Our exams will be in class, 2 of them, and then there'll be a final exam worth 30%. And I generally come up with, and I don't remember if I used to do it for this class, but I'm proposing that I'll do it for this class, that I will do this added thing here. I will take that number, and I'll put an optimizer in my spreadsheet. I'll say, we'll leave it like this, or we'll bump the projects up to 25% and take the final down to 25%. And I'll optimize on that. You know what I'm saying? I'll take the max of those 2 ways of doing it. And why would I do that? You're going to be turning in a project near the end of the semester. You're going to be studying for the final. And the project you have a lot more control over because you're doing it at your leisure to get it done. I mean, if you put it off, you're panicking just the same. Come in to take the exam, you can have a really bad day, or you can have a really good day. So that's why I let it go both ways. It might be that in the final you do better than any other in-class exam. It might be that you tank it on the last day. It might be that you're so nervous that your brain goes out on you. Has anybody ever had that happen? Okay. But you're still a professional at it, right? Because you've been doing this for so many semesters, but you just have this variability, and random variables, probability, that's part of communications theory too in a huge way. But so does that sound reasonable? So that's my plan right now. So we'll go through chapter 2, which is mostly review, but it's got some new topics in it. It's got, in particular, we'll introduce autocorrelation function, and we'll look at the power spectrum. We'll look a little bit at the Hilbert transform when we need it, and that's only when we have to do single sideband. And this is not something that I really spend very much time on. Single sideband is something that amateur radio people still use. A form of it is used in the olden days of analog TV, and it's still used in HD TV as well. It's just a means of being more efficient, and we'll learn about that when we talk about modulation schemes. We first do what's called linear modulation in chapter 3. DSB is double sideband. AM is amplitude modulation. Those are the foundations of the original analog, and they form the foundations of digital communications too. And then we'll jump into chapter 4, which goes exponential, nonlinear modulation. We do FM, frequency modulation, and phase modulation. And the foundations for that are the analog versions of that, analog messages, but then they become digital messages today, where we have discrete phases. We were talking about 64 QAM, that's digital version of quadrature, both phase and amplitude modulation together. And plain old BPSK binary phase shift keying just switches the phase by 180 degrees, but you could also look at that if you take the cosine of 0, you get 1, take the cosine of pi, you get -1. So you're really just switching it back and forth on this this real axis. That's the basics of digital communications, which when did all that stuff really get started? It started with, in my mind, it started with the space program because we were having to communicate to satellites early on. And, what do a lot of people that have background in this stuff do in Colorado Springs? They're working in satellite communications. It's just our bread and butter in this community for one reason or another. When the Space Command leaves, which I guess is now going to happen, I don't know what that's going to mean for the defense contractors in town, but we had a mention of cellular. You can do commercial cellular, Wi-Fi, anything else. But in our community, we work a lot with military applications, and it's kind of the way things work. We are going to take the break here pretty quick. I'm going to finish up a little bit more. So I have this chapter 5, baseband digital transmission overview. I have a chapter of notes on that, but I really pretty much integrate that into some of the things in chapters 3 and 4 and also in the project. So I'm going to get you some digital comm background. And then the last chapter is just noise sources and calculations. It's more of a bread and butter kind of thing that Dr. Song in electromagnetics would maybe teach on too, but it's in the book for noise figure calculations and link budgets and things of that sort. Things that are fairly mundane, but things that a communications engineer needs to understand. How do I supposedly close a link? And closing a link means that we're transmitting enough power, radiating it through space. We have an antenna that captures the flux. And yes, it is the same flux from electromagnetics, watts per meter squared. So we have an aperture on your antenna, an effective area captures that. That's received signal power. Does that signal power over the noise that we have from the front end and the noise in the front end amplifiers, does that overcome enough to get intelligibility? And intelligibility on audio is our brain being able to hear noisy speech, right? You've listened to a weak radio station, you know how you can discern a lot when you have a lot of noise in the background. I'll have you do simulations here to explore that. But digitally, we have the bits being decoded in error, so then we can have a bit error probability associated with that, and then maybe you have to put coding on it and other sophisticated means to bring it up without transmitting more power, but maybe you have to actually transmit with more power, put a bigger antenna on or whatever. You can also, if I stand here and visualize outside, what's up on the top of the bluff out there? The cell towers are up there, right? Yeah, and so they can put multiple elements. 5G allows you to have array combining going on cell sites now, and 6G will have that too. But so more sophisticated things. What can you have on your handset? You can't have a big, huge antenna on your handset. So there's limitations there. The disability services. If you need to do this, let me know. If you've already done it, I already know, at least for one person in the class. But if you still have yet to do this, please do it, because they asked me to put this on my syllabus. This is kind of like the law at UCCS, if you need to do that. Okay, Slack, you've already cleared the hurdle on this, mostly. I'm not sure everybody talked to me yet, but I think it's pretty close to 100% at this point. For Python, what I want you to set up, I prefer you to set up, if you haven't already done it, is a scientific Python based on Miniconda. That's my preference. And Miniconda, if I was to follow this link, if I can follow the link, it's not going to work today. Thought that was a hot link in there, but it's No, maybe it's because I've got this on. No, never mind. I'm not on the browser anymore. I was doing this last week. Is it because I had this turned on? Yeah, there we go. So this takes you right into Miniconda. Don't be thrown back by, is this in a commercial setting? You're in an educational setting, so just follow the instructions for an educational setting. This laptop that I'm on is new. As of a couple of weeks ago, I decided my old teaching laptop was over 6 years old, and I'm spending part of my huge bonus here for teaching to buy a $650 laptop. So I paid $650 for my laptop, and it's actually pretty good. I got it $350 off at Best Buy. As an experiment. Maybe it will fall apart. I don't know what happens, but at any rate, I'm doing this to testify that you can run stuff on a fairly lowly laptop. I have nicer ones that I like to use at home, but this one's pretty good. But you can follow the instructions on this. How many of you are going to be installing or have installed under a Windows 11 environment? Mac OS? Okay, I mean, I have it on Mac, Linux, and Windows. I actually have it on my iPad. You have to buy an application and run it on your iPad. But you can run it on an iPad too. I would recommend, though, because the one on the iPad crashes frequently, that you'd want to run it under Windows or Windows subsystem for Linux, which I also have on this laptop, or your Mac OS. And I will help you if you have issues with this. What you want to do is you want to go back to the website, and I have you covered on this. This link right here will take you into a document I call creating a new virtual environment under Miniconda. So you install Miniconda, then you follow down through this, and you're going to actually create a virtual environment, which will be a separate environment for just the packages I want you to install. You keep your base environment intact, and then if you host things up on your virtual environment, you just trash it and build up another virtual environment off of your base, which is in Miniconda. So I take you through that process here, and if we go like into the terminal, which is pretty much what you have to do, in Windows PowerShell, I'm running a Julia session here, but what will happen here, when you install Miniconda, you're going to get several options. You can bring it up in PowerShell or bring it up in the just the raw command line. I prefer PowerShell myself, but so I have a PowerShell prompt open up, and at the very beginning, I launched what I'm doing. I first activated my virtual environment, which the document I said talks to you about. If that's too small, I'll make it bigger. So I first typed Conda because I have Conda installed, Anaconda, Miniconda, they're all from the same company. So I activated the environment I created for Python 3.13, and then I immediately launched the Jupyter Lab and brought up a web browser. So I just typed up the command line, Jupyter Lab. So you could automate this more, but I use the terminal and command line stuff all the time doing software development, and some of you have never done this, maybe. Others of you have been touch and go on it, but don't be afraid of the terminal in Windows, let's say, or the terminal that you have in the Mac OS. They all work kind of similarly. So I've launched it, and all this stuff that you see in here is just stuff that's reporting out to this terminal window because I'm running over here. I'm running a session of Jupyter. Jupyter Lab is over here, right in this environment. And I've just launched it by searching for my one and only notebook. I'm just viewing its outline, which gets created automatically as you create a notebook. So it's a pretty nice way to go. If you do want to explore other things than what I have in here, this is like the core basic, just to get Python up. Everything's talked about in here. The other thing you can do, though, is if you want to explore Julia, you can go with this option. I call it Julia with Python. This, you start off and you don't install Miniconda. Instead, you install Julia to start off. And Julia takes you to another link that I think I have out here. That's in the syllabus. Got a lot of tabs opened up right now. Yeah, I have the link to the PDF we were just looking at. But Julia is just a language that's, like I said, it's a vectorizing language, just like Python is, and which MATLAB is also. Everybody knows MATLAB stands for Matrix Laboratory. That's where the name came from. Python added its equivalent to MATLAB with the creating of NumPy module or NumPy package, and then there's another package called SciPy. Then there's a third package called Matplotlib. Those three packages together form the core of what is scientific Python. And then I have a package that I wrote that's on GitHub that you can install directly, and it's in the instructions that are called scikit DSP-com. And it started when I wrote my dummies book. I wrote Python code because I wanted open source software, and the authors, John Wiley, didn't understand what I was doing. But one of the biggest things I got from writing my book was it got me into the open source software community and publishing stuff on GitHub and just getting on with that stuff. I mean, being a contributor. If you're going to use open source software, you should, at some point in your life, plan on contributing back. Does that make sense? It's an open source community, and it's actually fun. I mean, it's fun for me. I mean, in its own special way, of course, but every place I've worked, they use open source software. Everybody just takes advantage and leverages off of that. So if you did go with the Julia setup, you first get Julia set up, and then you go ahead, after you install Julia packages, you go ahead and install a package called Conda, which, if it sounds familiar, it's because it's Conda. Any Conda actually gets installed automatically under the hood. And then I take you down through the process in here of how to, you get a Pluto session up and running too, but then you switch over and go ahead and follow into this flow here, which sets you up with the same tools in Python running within your Julia install. And then when you get done, you can do everything with that environment. You can launch Jupyter Notebook to run in Python, or Julia in Jupyter Notebook. You can launch Pluto Notebook, or just use the command line interface to run Julia. And if you don't want to do this right now, I'm just throwing it out there. I put a lot of these documents up to help me because I go to different company, and I want to go to my website, and I get all my cheat sheets right there. And you guys do the same thing. You just have different cheat sheets, but you look for somebody that's done this, a help of some sort or another. And I have my own way of doing things, so I write stuff. And I'm going to write some more stuff this semester too for some of the other things I want to do in here. But to be very conservative, just look at what I have here. This will go for you. Last semester, everybody did it, and it all came together. Slack, message me. Bring your laptop with you next week. I mean, an assignment is to get these tools going. So you got Slack on your system. That was trivial, right? So now you have a little bit more of a challenge to just get a Python environment up. Is everybody taking that challenge on? You will be rewarded. And if you haven't done these things, maybe this is not what you want to do in your life, but it's been great for me. So what I want to do now, as we're approaching 9:30, is I want to jump back over to where we were. And we'll talk about this when we come back from break. So let's take about 15 minutes or so and just do what you have to do. Don't be late. I'm going to start. I'm going to pause my video right now, and then I'll resume it again. Okay, we're back live recording again. These recordings are made for you guys here in class in front of me, but people around the world watch anything that you put on the internet, right? I don't know why they do it, what they do with it, but I'm happy if they enjoy, learning some things. So the next thing we're going to talk about is the instructor policies. And I've always had the policy of being due at the start of class, but last semester I kind of modified this because of the fact that the reality is you're not turning them into me as paper, you're turning them in electronically. And I really don't like it by having you mess around with papers, even in that day of still working on your papers and you're trying to attend class and you're just, you're not focusing. So what I say on the first assignment sheet actually is not at the start of class, but by the end of the day that it's due. So if there's anything I might say that, like if today you were turning in papers, if there's any hints, any questions that came up, you actually have until midnight to get it pushed onto Slack. And I can see the dates when it comes into Slack, so I'm just asking you to get it delivered to me. If you are traveling on business or some other activity that's official in the sense it could be a death in the family, interviewing, I'd like to know beforehand if at all possible, because I'm just sort of writing you off. And what I'm doing is I'm putting up solutions. I want to post the solutions up there as soon as possible. And I don't want to have you be holding back the class. I want to know what's going on, and I will give you either I'll hold off or I'll just know what's going on. I know that your paper is still coming to me. The way that I grade will be on a straight scale with curving as needed. And so 70, 80, 90 is the thresholds, and that gets you to cross into the minus, like C minus, B minus, A minus, but that can always be bendable. And what I will do, I'm not using Canvas and its wonderful automated grading thing. I've never really gotten into that, and I could talk a lot about that, but it's called CMS, right? Course Management System. And I grew up writing my own web pages and doing everything on the internet because there was no CMS. And when it came into being, it was extremely unreliable. And I felt like this thing is just got to be driving students crazy. But you guys it's gotten much better, I guess. But sorry, I'm not going to be swayed into changing my style. So what I will do, though, is I will create histograms and keep you informed about what's going on. I have to push everything back to you, and you will get the score back from me if I've got it already on the histogram, or you can just see it on the histogram for an assignment or a collection of assignments. I'll eventually aggregate quiz/homework turn-in scores, and you'll be seeing an aggregation of sets 1 through 3 or something like that, and seeing how that distribution is unfolding. And then when you take the first exam, I will aggregate exam 1 with its individual histogram into a composite histogram, which will give a projection. And a projection is just a simple way of saying, hey, you've got 15% from the first exam, you've got a partial go at your 20% from homework. I can merge those two together, and then I can normalize by the 0.2 plus the 0.15, and then get it back to 100% scale, and then I can give you that histogram, and you can say, oh, I see that right now my standing is approximately thus and such. Is that helpful? I mean, because it's an evolving thing. It keeps changing right up until the last minute, and it generally either gets off to a slow start, usually gets off to a slow start. People are calibrating their style to what I'm looking for. And then things will generally, what will happen, and this is a probability thing or random variables thing, we'll see a wider spread, and then it will get more compacted, and it'll be gradually, I'm getting this backwards for your point of view, if this is 100 over here, it'll be spread, and then it'll get more condensed, and then it will gradually get higher and higher. And it goes sort of in the limit to the final exam grade. It still keeps moving in that progression. So I try to keep it, it's a moving target, but I can give you a static shot, a screenshot, and then you can see where we're headed, and I will say things to you like, it looks like thus and such is going to happen, but it's never known until the final numbers are in. But that's my way of doing it, and they will be pushed onto the website anonymously, just as a histogram, and then you will have your score, and then you will be able to see where you fall. And I really don't know what else you want to know, because you don't even know yourself how you're going to do from one moment to the next, right? It wanders around something, and that something is, maybe you're used to always getting in 85, maybe you're always used to getting in 95. I don't know anything about your performance in the past. And people always tell me they're spending so much time up for this class, but I don't know what to make of that either. But I do know that signals and systems is not a math lean subject. It's very heavy in math, and not a lot of people really enjoy this level of sophistication in a subject matter with all this math modeling involved. But I can say that for me, it's been a very rewarding career. What do you want to do with your day as working for somebody? Do you want to either do no work and get paid a lot, and that's not legal? I mean, that's sort of illegitimate. Do you want to be very satisfied that you're doing high quality work, it's challenging work, and you're making customers happy? And on top of that, I always say this to any of you: every day at work, with your chosen focus area, you want to have fun sometime every day. If you can't have fun sometime every day, you're not in the right position. You will have times when you're bored and you're grunting and groaning on things that you don't like, but you will have fun sometime of every day. Now, fun is a relative term. What do you call fun? Oh, skiing down a hill, nearly wiping out and killing yourself, or, lately I've taken up road biking. The last 3 years I've been doing rides for 2 weeks at a time with a small international club, and it's phenomenal to me. I used to backpack, and I used to enjoy backpacking, but this cycling has been a lot more fun for me lately. It's a very different thing, though. It's still something as abstract as being an engineer, where you don't really see the same fun stuff that you have when you get together as a family, or maybe go to a baseball game or sporting event or something. But it's still fun as you're enjoying what you're doing. And I can comment on, I've had a lot of experiences. So I will place homework solutions up ultimately, so that the evolution of a homework assignment is it's an assignment. It could get tweaked, and I will inform you if I've made a fix to something or something's broken. I will also give you a hints page eventually, and then after it's all turned in, I will give you a solution set under lock and key PDF that you can see everything that I did. And the exams will follow that same pattern. Old exams, then you'll take an exam. The old exams will be with solutions, and then you'll work an exam and get the solutions to that exam posted ultimately. Projects, not necessarily, because I've used projects in the past, and I just don't like posting up all this info because they're my thing, and I spend a lot of time developing projects and then writing out solutions. And you're going to say, when you see the first project, you might say, oh, this is so much work, but I'm going to give you a starting point. I'm going to give you a framework to build upon. In the last project, which we were looking at already, had a lot of block diagrams, had a lot of pictures, a lot of material was built, and it's built on Scikit DSP.com, the package you'll put on for Python. But I also have a lot of other things written to kind of glue it together, so I can make you do something fairly sophisticated by giving you a starting point here, and you just have to notch it up just a little bit, and then you'll get a flavor for what it's like to do this type of measurement on a system without starting at scratch zero. You can study how I built it up from there, but I want you to have some hands-on. The first experiment might involve, or project might involve, more building up. I haven't really decided. I'm thinking of changing up entirely what I did before, just because it was all analog based, but yet I haven't really decided on that either. I tend to think, even though we communicate digitally for almost everything, we still enjoy listening to streamed sources, right? If we're listening to music or talk, a podcast or something like that. So what I can throw on and what I'm thinking about right now is something that may have digital early on, but it will have an interface to decode the bits that go through back to speech again or voice, and that can be a satisfying thing. Have any of you thought of that? Because it's just a matter of decoding the bits, putting them into what's called PCM, pulse-coded modulation. We'll talk about that eventually, and being able to hear it. Now, it'll also bring to light the need to synchronize, something that a lot of you go to school, I think, all the way through, and you think, oh, these bits just come flying at me, and I'll just put them together, and I'll make sense out of them, just like that. What do you think? Is it that easy? You've got frame syncs. You've got other synchronization levels. So there's a lot of synchronization that goes on, more with digital comm than with analog comm, and that is daunting. That's where the control system comes in, actually. You have to track some unknown parameter like the frequency or the phase, and track amplitude too at times, automatic gain control. So you have to have these other tracking loops in there, or tracking means, so that you can kind of hold things together and then synchronize it and then get your packets out and decode everything to have useful something. Now, I don't know what you think about that, but I tinkered with radio and I could always listen to something. Think about digital, and you can eavesdrop to your heart's content, and what can you make heads or tails out of? You got to know quite a bit in order to get certain information extracted on most signals these days. And it's encrypted of necessity too. People don't want their information shared, but that makes things more daunting. But still, at the waveform level, we can synthesize things and know what our test vectors are and so on. Okay, what's the connection to the lab? Is that the lab is fairly tightly coupled. There's mostly using how it starts off with learning how to use the RF spectrum analyzer, and we use an RF network analyzer. And so we actually do some of the things that's done in the microwave measurements lab, which is in the electromagnetic side of the curriculum. But here our focus is getting at communications applications and seeing it be all integrated. So the first lab goes heavily into that. What does that look like? I mean, this is my sales job on the lab actually right now. So I go over to here, and you drop into the communications 4670 lab, and I've got two primary tabs in here. I've got supporting materials, which are helpful in doing the various labs with some of the components, but then the lab assignments themselves. So every lab has got a PDF document. It's Dr. Plett coined this term to me. It's called your lab reader. He was really big on readers, and some of you have had him for class. Did he ever use that in class? Reader? I guess it's a good term, but he was a fan of it, so I'll call it my readers. But people call their glasses the readers too, right? At any rate, so you have a lab reader, and then you have a sample notebook zip, which you can unpack, and then you use that for writing your experiment stuff into. And I've got an example of some of the things that come with the notebook. So I have a rendered PDF of that notebook just so you can see. And how do you create a rendered notebook? Well, we'll be looking at that eventually, but you can actually, through a few steps, you can render it out with your web browser. Is that render it down to PDF? And that's very useful for turning things in as assignments here too. So, and then I had a guy that ran this before Tarrant. He developed some rubrics, and they're useful too, things that he was looking for, he or she, depending upon. I don't think I've had any female lab instructors, but at any rate, the rubric is an example. It's not the final. What you hear from your lab instructor is the final on what the rubric is for the grading, but he might be following these. So let's just take a look at what's in this first lab. Measurements in the frequency domain is the focus, and the main focus is learning how to use the spectrum analyzer to take measurements in a 50 ohm characteristic impedance environment. And you're developing the spectrum analysis techniques based on Fourier series, which is what we're going to be getting into in the lecture, of sine, square, and triangle waves initially, and then some other pseudorandom sequence generators. And then there's also components that sit around a comm system that are filters typically. So you're going to learn about network analysis of analog components and using a vector network analyzer. So there's some network theory there based on circuits, again in impedance matched environments where you're driving from a Z naught, terminating in a Z naught, which is generally 50 ohms. And that then translates into measuring with S parameters. This course is not on S parameters. That would be microwave circuit design and some of the electromagnetics. The second chapter, I guess, I taught EMAG once for Dr. Song when she was on a sabbatical, and that would be the transmission line chapter. So what I want you, those in the lab, to think about is when you took your EMAG 1, you had a semester on transmission lines. You remember that? You're going to be thinking of transmission lines and how we connect signals together and drive them through different networks. And that material was started in, that background was created in that class, the way I look at it. You may have learned a little bit about it in circuits too, but you don't have to have a microwave circuits background. You're just going to be analyzing things that are pretty much already done for you. But S parameters, what are S parameters anyway? They're defined right here, but they're really incident and reflected waves. Does that sound abstract? You started with waves propagation in physics, right? Plane waves. A plane wave would hit an interface and some is reflected, some is transmitted. If it's not, if it's oblique rather than head on, you get a refraction and so on. Transmission lines don't have the refraction aspect. They just, very simple. Heads into an interface, goes on, bounces back. So like if you have a filter sitting here, we send a signal into it and we want to block some frequencies outside the band that this filter passes, it bounces it back and sends it back. It has to get absorbed at the other end of the line in the termination there. What transmits through the filter transmits through to the output. Now you're saying, that seems so bad. Why do we have to reflect it? Well, it has to go somewhere, right? And you have to reflect it off. If you had a lossy filter, you could absorb it all, but most filters are built with passive, or many types of filters for RF are built with passive components that are transmission line chunks or abstracted from transmission line from lumped elements, L and C. So the filters that you analyze in here are all L and C based filters, and they're designed in the S domain. I have some nice functions in the zip package for getting filter transfer functions from parameters, inductors and capacitors. You end up taking a bunch of measurements. You have these as the ladder networks, which you may have heard about in circuits, L and C ladder networks, transformations to bandpass, so on and so forth. And finally, I have some cool analysis functions so you can test filters and get their sensitivity. So down at the very end, you get to have this GUI in the Jupyter Notebook that you can tune. You're going to take measurements in the lab, and it's not going to match the measured. And you're going to be saying, oh, this is so terrible, right? But is that reality or what? I mean, nothing's perfect. Digital filters, yes. Analog filters, no. So you have losses. So you get to characterize it. When I built the lab, I was disappointed it wasn't closer, but this is an example. The top curve, with zero insertion loss, is what the theory would show, but then you can enter parameters in to basically make it more realistic. So I have sort of an inverse design problem here where you measure it and then you see each section of the filter. The tolerances on the capacitors are going to be off because of the percentages in those. And then the Q factor, which is the loss in the inductors primarily, but there's loss in dielectrics for capacitors. But at any rate, you can change the Q so you can kind of dial it in. It's kind of a cool, it's like playing a game, right? You're going to take a measurement and then you're going to try to see how you can make your theory match the measured. And it's a way of at least explaining why it's not perfect and how you could maybe design something by getting components that were more exact. Sound cool? I mean, I like it, but I created it, so I guess I should like it. If I didn't like it, why would I create it? So at any rate, all your measurements are done using the FieldFox Spectrum Network Analyzer, which is a small portable device, and all the board stuff. I'm just going to, a nice function generator for RF and programmable waveform types, 2 channels in that one. And then this is the board that I developed that has all the components on it to do filters with lumped elements, and then it's got other things for mixing or multiplying signals and splitting. This is 100% analog. This is not the majority of radio. It's just an example. It's something that you can play with in the lab, and it's very authentic in terms of the types of things you would do in testing equipment that you're manufacturing for delivery to the customer. I mean, I was in the lab last fall with my space radio, testing it, and I put a channel emulator on there, and the channel emulator emulated the fact that when the space radio is traveling through space, it's got a Doppler on it, and it's talking to another radio that's on a satellite, a TDRSS satellite, which is tracking data and relay satellite. You may have heard of that before. But at any rate, the vector that connects the 2 objects is actually it's either getting longer at some rate or getting smaller, so it has a profile called the Doppler profile. Everybody knows about Doppler, right? You've experienced Doppler. So that is a big impact on our space radios. In the emulator, it was just a box, and I could program it with a profile. I wrote code in Python and moved it onto the box, and it could emulate the movement in space without having to put the radio in space and putting it in motion or something like that. We experienced Doppler when you're talking on your cell phone or listening to the radio in your car. We built systems that can handle the Doppler, so that should be scary, thinking, why is it that it works with Doppler? Or why is it that it doesn't work? I mean, so we understand that from this class. What are the issues to deal with Doppler? It's, once again, in my view, it's very exciting to get into it. You have to be up for the challenge, but once you conquer that challenge, then you become competent, and then you're heading in the right direction to go work for somebody that builds systems for people. So I just took a look at that one lab. There's other things you do, more mathematical. This one is very much hands-on with the equipment. So back over to where we were. These are the rest of the labs. Probably the next one that I brought some equipment in for is software-defined radio, and I just want to pass these around quickly. These are 2 software-defined radios. They plug in through USB, and I just have 2 antennas on them, but I'll demo this one today. The first one that's in the clear box has got a transmitter and a receiver on it, and I will eventually demo that. And to demo that, I'll be using this GNU Radio Companion, which is a block diagram tool, and then I interface directly to the application running and can program it using blocks, DSP blocks. So if you're wanting to see pure analog hardware, you don't see it except at the endpoints, either the transmission end or the receive end, and that is kind of where we live, and that's the very nature of anything I can pull out of my pocket. I don't know how my audio is getting onto this system. I won't know till later, but last semester I was using these Bluetooth earbuds that I didn't plug these into my ear, but I just used the microphone and used those to capture the audio and it worked okay. It worked pretty good. I'm not passing this around unless you want to see it. I mean, most of you probably have.
Oh, like, oh, okay.
You want to pass it around? Everybody has one of these. I'm willing to bet something similar to that. That was, I bought that. It was what, a $20 or $30 item at Target or something like that. That's where I got it. So more comments in there. But I really think if you're a person that likes learning by holding things and connecting them and looking at instruments, you're not going to be working alone. You're going to have a partner you should take the lab. It'll reward you. Will it take time? Yes. So, you have to manage your time, but it'll be rewarding in the end. Will it be frustrating? Of course it'll be frustrating at times. I can't get this to work, but you won't be the only person in the lab, so you will figure out what's going on, and that's pretty much true of anything in engineering. Remember what I said, you don't start at scratch zero. You're always starting with some base to work on. And it's a legacy thing, unless you're on something that's totally new technology. Okay, software tools, I've talked about Jupyter and Python, and perhaps Pluto. I don't expect a lot of adopters of Pluto, but I will demo it at some point. I have a session running right now, but Jupyter for Python is pretty much a given. You can write markdown cells that include mathematics using LaTeX math, which, for those of you that took controls, did Dr. Platt ever talk about LaTeX? Never. Maybe? He wrote all his notes, and my notes are written in LaTeX too. Typest is a new tool, and that one I will demo. I don't think I'll have time today, but I'll introduce you to Typest at least. I'll bring up the webpage, and you can create an account on Typest, and then you can just, all the tools for Typest are right there in the cloud. You don't have to install anything. You can do it from any browser, any web browser. Push things up, pull them back down, push things up specific from a Jupyter notebook, or paste up graphics or whatever. It's to me, I learned about it about a year ago, and I used it at work for creating reports. I used it in both classes here. It's pretty amazing, because I don't like installing a lot of open source software. It's time consuming, and then a new version comes out, then you have to rev your version. Python tools, we can rev them once they're in place. Types, its environment is very nice. It's just excellent. It's a couple of Germans that have developed it, and they're trying to take LaTeX math and technical writing into a different realm. They're taking it up to the next higher level. And if I would have never stayed on working when I could have quit, but I don't want to sit around the house and do nothing except maybe ride my bike or run with my dogs. Those are probably my main activities for exercise. I learned something new, and I think you're going to be a learner all your career, unless you drop out of electrical engineering, and you'll learn something else probably all the time too. So what we do is, whether it's Python or Julia, we're doing analysis and simulation. All the environments are free and open source. Julia is the newer of the two. It's, like I said, it's about 10 years younger. So it's more formative. It's not as well established. NumPy came into the sights of Python back in the early 2000s. There was a guy that wrote a dissertation on that, and then the SciPy package, and like I said, the Matplotlib, the graphics was motivated by MATLAB's graphics, actually. You can kind of tell with the title, right? Matplotlib, so Mat is from MATLAB. I learned about that a whole lot more when I went to the Scientific Python Conference. The guy that developed that, the founder of that, sad to say, died at a pretty young age too, but he was the creator of Matplotlib graphics, which is pervasive actually in the community. Python is, I don't know if any of you that haven't learned Python yet, you're going to get a chance to try it out, but it's probably the most popular language there is right now. Would anybody else testify that from your reading or understanding? It's very pervasive. Why do I like Julia? What's Julia got over Python when it's less developed? It's very fast. It's very, very fast. You run a function once and it's got to compile it, but then you want to send a lot of code through in a radio or something. It's very, very fast. It's extremely fast. So that's where it's got an advantage. But you don't necessarily see all that advantage if you're just running some code one time through. I've done a simulation project for a company in California in Julia, and it made a huge difference on what I was required to do for my work for that company, and I could deliver it to him in open source. MATLAB, seats of MATLAB were just too expensive for him to buy from me. And I used to use Octave, which is available for free, and it's like a clone of MATLAB, but much less than MATLAB for sure, because it's totally free. I don't really recommend Octave anymore unless you can't break out of using MATLAB. And Doctors Platt and Trimboli are still steeped in MATLAB tradition. Companies in town are steeped in MATLAB tradition. So you will maybe work for a company that says, yeah, we did it all in MATLAB. You'll have to jump back over to that. But Python is becoming and has become over the past more than 10 years. My Dummies book was written over 10 years ago, and it's changed a lot. That's when I started using Python. Now I've used it for over 10 years now. It's changed tremendously. Things have grown up tremendously. AI is behind. I mean, it's right in the hot seat pretty much of where everything is happening. Okay, you can't forget about your calculator, because that is what you're going to have when you take a quiz, if we do quizzes in an exam. Sorry to say you can't have Jupyter on a homework assignment, on an exam, but it's just one of those things. I haven't figured out how to eliminate that. And hey, I bring up a quick example of where a student got caught cheating by me quite a few years ago in an exam. He went up to take a couple bathroom trips, which I thought was unusual. A couple, one I can understand, but two, and he didn't come back for a long time. And then later I had a graduate student who was in the computer lab, and he said, I think one of your students came in and he was browsing, and then he came back to class, and I found about this later. And then I confronted him. I said, I have evidence, I have the web history and all that other stuff that you were going to the course materials and everything just like we have here. And he confessed and got a 0 on the exam. But so I know how easy it could go out of control because of somebody walking out to go. And I didn't say this to give you any ideas. I'm just saying that things do happen. I'm not sure it gave any advantage, but it's hard to say what to do. I want you to experience the tools, though, because it's not normal to sit and take a closed exam. You'll have a cheat sheet, you'll have a crib sheet, and so on. But I thought I'd bring that up. And that I'm going to time out here probably, but I just want to jump back over to the website again and say that if you're wondering when I said crib sheet, go back over to here and go back to our class under course materials. All of you will get to have this printed for taking exams and quizzes and so on. It's just there, whatever we do, and you will have it too. I can either make your copies or you can make your paper copy, but you will want to have a paper copy of this. So do you want me to make you one and bring one in, or can you get your own, print your own? It'll just be one of your warm, fuzzy things to hold on to, your security blanket when you take the exam, because it has the Fourier information on it, trig identities. This class, we use a lot of trig identities to help write out some of the simple modulation stuff. Now, trig identities, when I was in high school, I wasn't planning on becoming an engineer. I was kind of lost with all the trigonometry stuff. It was like, what am I going to do with all these trig identities, and will I use them? I use some of them, and I look them up all the time when I need things. I use lookups, to do stuff. So don't feel bad that you don't know your trig identities, but they do pop up fairly often in this class, and we will use them. Not extensively, but they are used. Euler's identities are used all the time too. It's just stuff that we do. We're always dealing with the math side. We're dealing with the Fourier side, which my experience is that most students are not as fond of Fourier as they are of Laplace transforms. Fourier is just plain messy because you've got the J thrown in there, either the J2 pi F or something like that. FT. So COM2, I'm not going to spend much time on this because I don't have the time, because I want to start in the lecture. It continues, it's a continuation of this class. As a matter of fact, the Zemer and Tranter book moves right on from this class. And I've always taught out of Dr. Zemer's books because he was my dissertation advisor. He wrote new editions while I was his student and while he taught here. He's the reason why I came here because he moved. I was at Missouri S&T, which some of you maybe have heard of. It's Missouri School of Mines. My school that I got my degrees at was Michigan Tech, which is in Upper Michigan on Lake Superior. If you like remote, snowy country, that's a place to be. It started out as Michigan School of Mines. Does anybody know why there was a school way up in the Keweenaw Peninsula of the Upper Peninsula of Michigan? Anybody know the history of that part of the country?
It started in World War II, right?
I think. I mean, I lived in a dorm that was built during World War II, actually. It was built in the 30s, I think. But what was up there? Does anybody know? It's historical, and it's a mineral. No. Take another guess.
Cobalt?
No. It's copper. They mined copper, and what was interesting about that part of the country, and as a student investigating the railroads and other mining equipment, it was off limits to students, but we still snuck around the old mining structures. They could have killed us if they would have caved in on us, but mines were underground. But what they mined was native copper. So the copper was right in the rock. They didn't have to smelt it like they would do down in Arizona or something. You just take it out and stamp it, and the copper would fall out, and the rest of the material would, they could separate the two very easily. It was very efficient, and they mined massive amounts of copper just by hauling it out and stamping it. So there's a lot of sands and things around Lake Superior that are covered with the tailings from the crushing. Mining is messy, right? It's up in Wyoming. All the coal that comes down from the pit mines up there. I don't know how you feel about it. We're engineers, mining engineers. We're at Michigan Tech. That's how the program started in electrical engineering. In a primitive way, started there because they had to have electricity for the rail and the lighting and the other things that go on underground in a mine. Pretty cool. Far field from this. They probably had simple communications going underground, but so that started Michigan School of Mines. I think it's lead mining in Missouri, where I went to school to get my doctorate. My wife went to Colorado School of Mines, and that's different types of mines, gold and other silver, other minerals and stuff that are in this state. Mining schools have a deep tradition, but, and I guess it's coming back. I read in a news blog that I get on engineering across the country that mining schools, some of them are reopening again. I really don't know, but when I was a freshman, my resident assistant, and you guys don't all have to live in dorms, but I was remote. I was 5 hours away from Wisconsin, near Green Bay, where I grew up. My resident assistant was from Peru, I think. He was a mining engineer. He was going to Michigan Tech because he was learning mining. Beyond that, I don't remember, except that he was a fairly funny guy, and his English and his lack of clear English made him a more interesting personality to me as I guess I'd say an impressionable freshman. You guys aren't freshmen anymore, so your impressions of upperclassmen and things are probably all faded out of your head. It's like, that person was good, this person didn't know what they were talking about, but whatever. I diverged once again.
Mining schools offer courses on explosives too.
Yeah. As a matter of fact, I had to take a mining first aid class. That was a requirement. That was still in the curriculum when I was there, so I had to learn about bandaging and other things. It wasn't all that critical, but I had to take PE too. And back in those days, you had to take so many units of physical education, which definitely is not very common anymore. So I took golf. I learned about golfing. I took bowling because bowling was easy. In a winter school, you could be in a bowling alley doing bowling, and when it was snowy, it snowed every day at Michigan Tech, 300 inches of snow, rotary snow plows going through the streets of the city, a very different area. Downhill ski area at the school, cross-country ski trails at the school. Very different kind of environment. So you learn about digital communications, and we will learn some about it here. We'll do the same modulation schemes, but strictly digital. But like I said, we're going to learn about them here to some extent because they spin up off of the analog techniques. Coherent versus non-coherent. That's another layer of synchronization. If we can get by with what's called a non-coherent scheme, we're much simpler, but we suffer performance-wise. We get better performance and noise generally with coherent. And simply put, coherent means that we can track the phase and frequency of the carrier signal that the waveform's coming to us on. We don't know exactly what it is when it arrives because it could have Doppler, and it's just going to have instability because the transmit and RX oscillators have some variation. They're generally controlled by crystal, and that crystal only has, say, 10 parts per million stability. Multiply that up to a much higher frequency, the 10 ppm, and say 10 megahertz or something, and then it's a bigger variation. At any rate, we can track the carrier. So we have a tracking loop, or tracking means to coherently track the carrier frequency and phase. That adds complexity. As a matter of fact, in the beginning of radio, they didn't even think about coherency. They came up with strictly non-coherent schemes because they were simple and inexpensive. Mobile radio channel gets talked about more, satellite communications talked about more, and then introduces coding theory. I pretty much deal with satellite communications in the work that I'm doing since I left teaching here full-time. But I did that part-time. I always worked in different companies. I worked for a lot of different companies. Some of them have merged. Kratos was Real-Time Logic, and then they got bought. I worked for them on a sabbatical, and then I worked for them when they were Kratos. I work for ARCA right now. ARCA is emergent in Colorado Springs, but ARCA is a company that bought a number of tech companies. And I worked for a company, a division up in Washington State, which has now moved all its labs to the ARCA building in Colorado Springs. That's where I worked for Blue Origin on that project. It's a throwback for me because I worked in space communications when I first graduated. I worked in optical communications with my master's degree, free space optical, not fiber optic, but I worked in fiber optic some too. So that's why I like talking to the guys that were installing the fiber in my neighborhood. It was intriguing to me. Okay, now we're finally going to get in for 10 minutes to some of the overview. I should be able to finish this. So fundamentally, this is right out of the book, I think. Theory of systems for the conveyance of information. Any and all types of information. It can be an unintentional conveyance of information. Think, for example, a country, China or the Soviet Union or Russia, is detonating a bomb underground to test some nuclear weapon. What's that going to produce? It's going to produce some seismic waves. What can we do over here? We can intercept those seismic waves. We can determine things so that, or a plant or animal maybe is emitting something. I studied bats with students here at the Cheyenne Mountain Zoo. We put an experiment in the bat cave down there so you could listen to the bats echolocate. And that was a fun project to work on, bats echolocating and how excited they get when a piece of cantaloupe got hung in the bat cave. And they were echolocating like crazy because they're all trying to get that fruit at the same time and not run into each other. And I learned some things from it too. Maybe I'll play an interesting audio recording that I got of a single bat echolocating in the bat cave. There's radar principles are based on things I think the bats have done since they were created. I mean, how they echolocated and how they could, know where the walls were and objects were. It's kind of cool. So I'm just saying we don't have to put up a transmitter and a receiver of our own doing. We can have it be a one-directional thing. I worked on laser comm down at White Sands Missile Range, and the other side of the laser communications free space was lasers that would blow things up or, destroy things. So whenever we tested, we had to tell the range commander we're doing a test over the desert floor, down to Amir and back. they wanted to know because other experiments that were going on at White Sands Missile Range, I think, probably were high-power laser devices. And the road that I went on, this is just a really trivial thing, but the road that I went on when I went into the range went further north, and the sign I would go by on the way to my test setup in the desert was the Trinity site. How many of you are familiar with that name from history? That's where the first nuclear tests were done, further up the road. So it was an eerie feeling for me to go there and see that sign on the road. It's like if I drove a lot further over a desert with sagebrush and, minimal plants, that's where something else happened many years ago. So, has anybody ever been to White Sands? It's an interesting place to visit because it is white. It's not brown. There's an Air Force base there. That was part of my project, Holman Air Force Base. Okay, so focus on deterministic modeling, but we will bring in noise, especially in simulation models. It's so easy to do in Python. So a little bit of history, and this is just from the book, so it doesn't go super long, but telephone line in 1915 for Transcontinental Railroad. That's quite a ways back. Armstrong, somebody who's very famous, and it's explored in one of the labs because we have some radio modules, hardware modules I designed and you'll play with in the lab. He developed a superheterodyne radio, and we'll talk about superheterodyne. It's a principle of mixing or multiplying signals and what it does with RF. It's still in use today. And Armstrong went on to do other things with his career. He's the pioneer of FM radio. And it's a sad story because AM radio took off first, and then Armstrong and his FM radio idea, the founders of the big AM radio stations on the East Coast I think they discredited him and did some other things financially to him, so he ended his life in a financial ruins. But he was a great inventor, and I think you look at history. I used to teach a class here called Radio Electronics for Non-Engineers. It was a general ed class, and I don't have that back on my website yet. I may put it back though, and they had to write papers in that class, so they would pick different pioneers of radio to write a paper on. Television broadcasting in 1938, World War II is when radar and microwave systems got their launch. There were vacuum tubes initially, and then in 1948 the transistor was invented. First transoceanic telephone line, 1956. Laser in 1960. Communication satellite in the U.S., 1962. So that's why when I say the 60s, all the SATCOM stuff that I'm involved with and projects I've worked on over the years, the first generation of developers and engineers are essentially gone. I mean, there's a few legacy people that are very old, but we're carrying on a tradition that's really not that terribly old. Fiber optic in 1977. I worked on a project called, I don't remember what the name it was, but its byline was Switchboards in the Sky. It was going to be a satellite that rather than being a simple bent pipe up where it goes up and gets transponded back down, it was going to be a satellite that could reroute and be like a switchboard in the sky. And I think we have some satellites with that capability today for sure. GPS came along in the 90s. I've worked in GPS quite a bit. I worked in cellular telephones. That came around in the 90s. Global satellite communication system. The first project was the company I worked at in Arizona was the Iridium system. I worked down there in the LaserCom program in Scottsdale for a company called Motorola Government Electronics, which is now, aerospace company that's here in town too. The name's slipping out of me. They're originally known for submarines, but I can't think of it right now. At any rate, the place I worked is still down there, and they're still doing things in satellite communications, because when I was at Kratos, I was working on a project that they were sponsoring. Smartphones, 2000s, when this book was written, we were in LTE, fourth generation cellular. We're now in 5G and 6G, and this keeps going and going and going. All communication systems will have some sort of input transducer. It might be analog, it might be purely digital. It will go to a transmitter, like the block diagram early. It will get reconfigured to form a transmit signal that can go out as RF or drive a fiber. There'll be a channel. We talked about the channel a little bit, noise, distortion, jamming, etc. Comes along, hits the receiver, gets converted back to some other signal format, and it might go through a transducer, which would convert it back, say, to analog, or most likely digital. That's sort of a generic, very high-level block diagram. Most of the time, the carrier is RF, and if we, turn and face that direction and go outside the doors, we would look at what? What's down south? The mountain down south is Cheyenne Mountain. And what do you see on the top of Cheyenne Mountain? You see all these sticks, right? The antennas. So I was going to run a demo with my software-defined radio, which is in the back somewhere, so I'll do that next time. But matter of fact, this dongle will come off. I'll plug the radio in, do a demo of that next week. This is a little bit of discussion that I will have. I'll have to start up here, but at the very end of this, which isn't too much further, I have the OSI model, and when I was talking about, here's the SDR I didn't get to, but this is an example from quite a few years ago. This was like the smallest radio that I found an article on. You could implant it somewhere in your body, and this radio is implanted into your eye. And it would be for measuring for glaucoma patients, where you could measure glaucoma pressure with a device that would energize its battery, charge it up, and then it could send back a pressure level. This is an integrated circuit device, so if you're into solid state, there's discussion in here about how it's built. I thought it was pretty cool. It's very low power radio system that would be in your eye. Am I excited about that, having placed in my eye? No. I did have thumb surgery last November. They took a bone out because of an arthritis issue. I play bass trombone. I play music a lot, and I wore my joint out. So then I had an artificial tendon put in here, drilling a hole and putting a tendon in, and I was done when I was under anesthesia, but I'm feeling pretty good. I have 2 scars to show for it, but I'm bringing that up because it's like I do have an implant in my body now. I have to think I do have 2 little metal buttons and this thing called a mini tightrope, because the bone removed was the trapezium bone. Trapezium sounds like trapeze, and the medical device they put in me is called a mini tightrope. So you get the dry medical humor, a tightrope to go with a trapezium that's no longer in my hand. I don't know. It was interesting. I'm pretty happy with it, though. Doing weights and things, and it's doing well enough. I'm going to sign off at this point, and I want to walk up to the lab because some of you are going to go up to the lab. If others of you